Okay, why don't we start? So welcome to today's class. We're going to be talking about pigeonhole principle, which is a very important topic in Olympiad, especially in combinatorics. So first of all, I will go over what pigeonhole is. Should be an L, not a T. So basically, the name pigeonhole comes from the idea of putting pigeons into boxes. So in the old days, what they had was mail pigeons. So when you send mail, you send the mail through pigeons. And basically, what they did was to store pigeons. They had little boxes to put the pigeons in. Hold on, my screen is kind of So anyways, you would have these boxes and you would put pigeons into them. So basically, the idea behind pigeonhole is if you have something here we have 16 boxes. If you had 16 boxes and you had 17 pigeons and all the pigeons were in the boxes, then you must have a box with two pigeons, right? So you must have a box with two pigeons. And sorry, my screen for some reason is not really working. So anyways, so the reason for this is because, well, you kind of have to use common sense, right? Because if you have 16 boxes and there are 17 pigeons in the boxes, there must be a box with two pigeons, right? Because if every box has at most one pigeon, then you can't have 17 pigeons. You can have at most 16 pigeons, right? If every box has at most one pigeons. That is the basic idea behind pigeonhole. And so in general, basic pigeonhole would be similar to when we had our basic induction and strong induction. We have our basic pigeonhole. And we have our strong pigeon. So I'll briefly go over what those are. So pigeonhole is basic. My screen. So basic pigeonhole. It's like what we just talked about. If we have something like K. Hold on. My screen is a little acting up today. So if we have K holes, and K holes and K plus 1. Wait. Okay. Hold on for a second. Let me get a new stylus. Okay. So if you have K holes and our boxes, we use the term hole instead of boxes in pigeonhole for some reason. So if you have K holes and K plus 1, there we go. K plus 1 pigeons. Then there is one box, a hole, with two pigeons. Right? That's what basic pigeonhole is. Okay, my screen is, I don't know what's happening. So strong pigeonhole is if you have something like K holes. And you have A times K plus 1 pigeons. Okay. Then exists, the backwards E just means exists. A hole with A plus 1 pigeons. And this is kind of like the same common sense argument. This is the same common sense argument because if you have A times K plus 1 pigeons, then if each box has at most A pigeons, then you can have at most AK pigeons, which is not true. Wait, let me. And so in reality, pigeonhole is kind of just common sense, right? Because it's really not the basic idea behind it is, it's just logic. It's not really hard at all. But it is still an important concept because it's very basic, but it's it's at the heart of a lot of problems, right? And it's not so much as a technique as a sort of theme that comes up in a lot of problems, especially combo problems. Like I would say most of the strategies in combo problems are actually just common sense, right? Like just like Pigeonhole is just common sense, but they are very important. Okay, so let's just get into some basic examples. So let's say you have like n plus 1 numbers. This is like a very simple example, n plus 1 numbers. Okay. And my screen is a little weird today. So if you have n plus 1 numbers, wait. If you have n plus 1 numbers, and so like, I don't know, so we want to show, hold on, let me show exists two numbers, a and b, from our n plus 1 numbers, where n divides a minus b. So the idea is basically you want to find two a and b that have the same remainder when you divide by n, right? So if like let's say a equals has a remainder of r, so like let's say a equals a prime times n plus r, and b equals b prime times n plus r. Well, since we have n plus 1 numbers by Pigeonhole, there must be two numbers with the same remainder r, right? So in here we see that a minus b would be a prime minus b prime times n. So it would be divisible by n. And I would say that sometimes this comes up in number theory quite a bit. So when you have like maybe n plus 1 numbers, then you know two of them have to be like the same remainder mod n. So this was a simple example, but this kind of logical thinking shows up quite a bit. Let's see. Okay, so here's another I would say pretty basic example. So let's say we have a graph, or not a graph, I should say n people at a party. It's basically a graph, but like we're just gonna use the flavor text. So we have n people party, and so we want to show that two people have the same number of friends, and friends goes both ways. So it's basically like a graph with n people, and the friendships are edges, and friendships go both ways. And we want to and so we want so like we want maybe like person x and person y have the same degree, right? They know the same number of people. So basically, if you have n people, what can the degree look like, or how many friends can they know? So of course you can, it has to be between 0 to n minus 1, right? Right. So first of all, you should notice that the degree has to be between 0 and n minus 1, right? Because if there's n people at the party, you can know at most n minus 1 other people. And of course, you have to know at least 0 people. It doesn't make sense to know a negative amount of people. And what you notice is that this is already n numbers, right? So since we have n people and there are n different values for the degree, well, you may ask, what if you just have one person? Well, this is already very close, right? Because we want something like there are only n minus 1 possibilities, because if there are n minus 1 possibilities, then we can use that as our holes and the n people as our pigeons, right? And just use Pigeonhole. But right now we have n numbers and n people, so that doesn't really give us anything, right? But the one counterexample to this problem would be every person has different degree, right? And since there are n degrees, there are n possibilities for the degree. Each person must go into exactly one of the possibilities, right? So that means you must have a person with degree 0, degree 1, degree 2, degree 3, all the way to degree n minus 1, right? So this is the only contradiction. but this is not possible because if someone knows n minus 1 people, then then you can't have 0 and n minus 1 at the same time, right? Because if someone knows n minus 1 other people, that means they know everybody else, and that means that everybody else knows him. So that means you can't have anybody with 0 friends. So 0 and n minus 1 can't be together. And so this would not be possible. So we have our pigeonhole as normal. Another common example is if you have 5 points on a sphere, show that 4 of them must be on a closed hemisphere. Okay, so when you first look at this problem, it's not really clear like what to do. I don't know why my screen is like this. Oops. Okay. So, we have our sphere. Wait, why is my screen? Okay, I don't know what's going on with my screen. I'm sorry. And we have like 5 points, and we want to show that 4 of them must be on a closed hemisphere. So basically, what a closed hemisphere is, you have like it's kind of like a semicircle, but you have like half a sphere, so it would just be something like this. And you include the boundary. So like this boundary around is also on the sphere. Okay, and so what you do is you take 2 points, 2 of your 5 points. Like I'm gonna use a different color. Let's say these are your 2 points, right? So basically, what you want to do is you want to draw a diameter through these 2 points. And on a sphere, if you have 2 points, that determines the diameter, right? Because if this is your center of the sphere, then you draw the plane that goes through these 3 points, right? 3 points make a plane. So the plane that goes through these 3 points cuts the circle or the sphere at a circle. And since this circle goes through the center, like the plane of the circle goes through the center of the sphere, it's the diameter of the sphere, right? And if you look at the other 3 points, well, by pigeonhole, you have 2 sides, right? Like you basically split this sphere into 2 hemispheres. And there must exist one side with 2 of the 3 points, right? This is just like common sense, but it's like also pigeonhole. And you basically just choose this hemisphere on this side. Yeah. Yeah, it seems like the video is a little bit laggy for some reason. I don't know. Okay. Okay. Let's move on. Okay. So we have our numbers 1 through 126. And what we want to, and we have 7 numbers from 7 numbers from this 1 through 126. And we want to show that there are 2 numbers from these 7 where x and y from 7 from our 7 numbers where 1 is less than y over x is less than or equal to 2. Okay. So anyways, first of all, how do we like capture this information in terms of Pigeonhole, right? It's not really clear exactly how. But one thing you can notice is that 126 is approximately 2 to the 7, right? So maybe we want to use that somehow. And the thing is, we can kind of use that. So if we have like a number x, right? Well, for we don't. So what we want to avoid is we want to avoid 1 is less than y over x is less than or equal to 2. We want to avoid this, right? So if we're avoiding this, then y is not in x plus 1 through 2x, right? So we don't want something within x plus 1 to 2x. And if you phrase it in terms of this, then then it's like this is pretty strong, right? So if like we have x, then we don't want something within x plus 1 through 2x. And this is pretty strong, right? So this kind of hints at like how we can kind of like do our pigeonhole. So we have 7 numbers, so we want to divide this set into 6 subsets. And then if two numbers are in the same subset, then it must break this, right? It must become this. And it's kind of clear how to do this subset. So like if you make this subset x plus 1 all the way to 2x, right? If you have 2 numbers from this, if a and b from this, okay, from this, then, and like a is greater than b, then it's clear that b over a is greater than 1 is less than or equal to 2, right? Everybody sees this because we have our numbers x through 2x, right? So this is a good idea. Anyways, can we partition 1 through 126 into sets like this? Well, we have to use the fact that like 126 is close to 2 to the 7, right? Because this basically takes us from x to 2x. So if we go backwards, like if we have 126, then we can go to 63 to 126, right? And this is very nice. So yeah, 60. If we have 2 numbers between 63 and 126, we're done, right? Like it kind of breaks our y over x is less than or equal to 2. And the next set would be 62 through 31, 30 through 15, 15 through 30, I should say, 7 through 14, 6 through 3, and then 1 and 2. And these are our 6 sets. 1, 2, 3. And we finish by pigeonhole, right? So if there are 2 sets, there are 2 numbers in the same set, and using our previous argument, then these 2 numbers must kind of break our hypothesis, right? So in this problem, we kind of did pigeonhole backwards. We started out with the assumption that since 126 is kind of close to 2 to the 7, right? We want to use some kind of pigeonhole argument because it's really difficult to do this without some kind of like thing that's similar to pigeonhole. And from there, we kind of had to construct our holes to match the pigeons, right? And that's one of the difficulties of pigeonhole, right? You can't just blindly plug it in. You have to figure out what your holes are before you can apply the pigeonhole, right? And that's the main difficulty with pigeonhole. Okay, I guess we can move on. Okay, so here's a fun example. If you have a set M of real numbers, it's the union of some disjoint intervals with total length greater than 1 show that there are two numbers with difference as an integer. So if we have our number line here, if we have our number line, then m is basically some intervals, right? So if you remember what intervals are, it's something like this. It's like some like it's like some numbers like I'm just gonna say x and y. So all numbers between x to y for some reals x and y. So we have a bunch of these intervals, right? And there could be a lot of intervals. We're not given how many, but the point is the sum of interval lengths. We can like interval lengths is just something like here, like the length would be y minus x is length. So the sum of lengths is greater than 1, right? So we want to show that there are exists two numbers difference integer. And when you look at this problem, you may think that it's similar to the first one that we did, right? Remember, if we had n plus 1 numbers, and we have exactly and we want to look at it mod n, and we want to see that two numbers have a difference that's a multiple of n. Here we're looking at a set of reals, and like the length of all the numbers, or like the size of the set is like greater than 1, right? It's kind of hard to define size here because like it's not like a set in the normal way you would think. It's not like a finite set. It's like you have infinitely many numbers, right? But you're given that the length, or I guess you could say the measure, if you want to be like, I don't know, if you want to go on some measure theory, the measure is greater than 1. So or I'm not actually sure if I'm using the term measure correctly, but anyways, we want to show that there are two numbers with difference as an integer. And we can kind of consider this mod 1, right? Like what if we just considered it mod 1 like we did before with mod n? So what do I mean by this considering mod 1? If you have something like x to y, and x and y are greater than and let's mark our integers as well. This would be like integer n, and this would be n plus 1, right? Then what we do is we only consider the fractional parts, right? Like we only care about mod 1, or in this context, mod 1 would be like you only care about the fractional part. So here we would only so basically what the fractional part is if the fractional part we use like this. This is like the symbol for the fractional part equals x minus floor of x. Floor function is basically the greatest integer that's less than or equal to x. And so like if x would be something like, if you write it in decimal form as like let's say a point I don't know, like 1, 2, 3, 4, then this would be the floor of x, and then this would be the fractional part of x. And we only care about the fractional part of x because we're only considering kind of like mod 1, right? So if we mod everything by 1, then what happens is we collapse the number line into just 1, 0, and 1, right? So we have our 0 and we have our 1, and we have a bunch of intervals, right? We have a bunch of our intervals as normal, kind of like when we had our like, so this would be like the fractional part of x to the fractional part of y. And here we know that the sum of the total length is greater than 1. That means that you must have two intersecting intervals, right? Because if none of the intervals intersected, then you could not have a length greater than 1, right? Because you must have some point that's covered twice. And if you have a point that's covered twice in two intervals, like right here, then if you take the two numbers that those sets correspond to, then their difference must be exactly an integer. So from here, we're done. Okay. Why don't we do this example? So if we have a 4 by 7 square, let me just draw this really quick. I think I made this a little too long. Anyways. Yeah, if you have a 4 by 7 grid, prove that if you color each square, color each square red or green, then exists rectangle, same rectangle, all vertices same color. By rectangle I mean something like I'll use like yellow so it's not red or green. So like something like 4 vertices like this. So like you have your rectangle like this. And like all these 4 points are the same color. So first of all, what happens if we have, so the idea is, first of all, we look at the columns, right? So the columns are pretty important because they're kind of small, but they're pretty important, right? It's just like each column is like a 4 by 1, right? And what happens if all 4 are red? Like, right, what if we have 4 that are the same color? Well then if you have like your R's here, R, then another column you cannot have 4 reds, right? Or sorry, not, or you would have less than, or you would have at least 3 greens here, right? Because if you have 2 reds, then that like kind of makes a rectangle, and we want to avoid those. So like let's say we have 3 greens here, and let's say we have another column, right? Because we have 7 columns. Another column here that also has 3 greens. Let's say here, here, here. Well, what you notice is that no matter where you place these 3 greens, you're always going to have like a green rectangle. If you just like kind of think about it, you always need to have a green rectangle, right? So you cannot have you cannot have a column with everything the same color, and you can also not have you cannot have two columns with 3 greens. So let me write that. Not a column with 4 same color. Not 2 columns with 3 greens. Or reds, right? It's the same, like the 2 colors are basically the same. Okay. So the next case we should address is what if we just have 1 column with 3 greens or 3 reds, but we'll just do 3 greens because it's the same. Let's say we have G. I should probably use the colors themselves. Why not? Red. Well, if you look at another column, what can the other columns look like? So the other possible columns would be like 2 reds, right? But we have to be careful not to like have we have to be careful not to have a green, 2 greens on top. So like let's say if we had two reds and two greens, so this would be 2R, um, two greens, then we must have something like a green on the bottom. Let me use the color. We must have like something like this, right? Um, like a green on the bottom and two reds on the top. Or we can have something like three reds and one green, right? But the point is, unless you have, if you have at least two greens, then the bottom thing must be green, right? So like, let's look at the other possibilities of the columns. We can have something like this. If we can have three reds and one green. Doesn't matter where they are. Right, but anyway, so how many, and we know that we can only have at most one column like three greens and one red, and we can only have one column at most one green and three reds, right? So and now and we can't have any columns that are all the same color, right? So we need at least 5 of these guys. But the problem is, you notice that here in our choice of colors, if you have something with two reds and two greens, let me just draw this again. A column, two reds and two greens, you must have the bottom is green, right? If the bottom is not green, then you have two greens in the top three, which is not good. And you must have the second one is red, right? Because if the second one is not red, then you have two reds that correspond with these reds, which is not good. So you can have at most 4 of these, which is not possible, right? So you can have at most 4 of these. So like this is not possible. Okay, so our last case would be, what if you just had, if you only, if all columns are, wait, why am I, okay, so all 2 reds and 2 greens, right? Then what would happen? Well, the good thing here is that you can use Pigeonhole, right? So how many ways can you have 2 reds and 2 greens? Well, you can have exactly 6, right? So there are 4 choose 2. Equals 6 possibilities, right? So by Pigeonhole, we must have 2 columns, same columns, like exact same columns. What do I mean by this? Like you must have something like 2 columns that are exactly the same with each other. Let me draw this. So like something like, if you had something like G, G here, you must have like G, G, and 2 R's in the other places. And this is obviously bad, right? You can't have this. And so we're done here. And if you look at a 4x6, it's actually, the problem statement is not true, because if you have 6 different columns, each with 2 reds and 2 greens, then you would not have a rectangle. So 7 is very tight. Let's see, what other problems? Okay, I think this problem is good because it like kind of shows another important aspect of Pigeonhole that shows up a lot. Okay, so I think first of all, let's start with a very simple example. Let's say we have numbers A1 through AN. Wait, yeah, we want A1 through AN, right? A1 through AN. We want to show exists I is less than j, is between 1 to n, where AI plus all the way to uh, all the way to plus AJ um, is divisible by n, right? And we want to kind of use the same thing as before with our mod n, with like the pigeonhole, right? But here, if you notice, you have something like this would be n choose 2 possibilities, right? And the thing is, if you take two, like, if you take two of these things and you subtract them, you don't always get like a valid thing, right? So like if you have like a n minus 1, a n minus 1, if you have something like a n minus 1 plus a n, uh, and you subtract, and you like subtract this by like a1 plus a2, wait, well, this is not good, right? Like these are two sequences, like these are two valid sequences, but they don't, like when you subtract them, it's not good. Yeah, I'm sorry, my screen is not very good today. I don't know why. And if you subtract them, you don't get a good sequence, right? So you want to do something more clever. And the clever thing you want to do is you want to define like a different type of sequence, which is SI, a partial, this is called a partial sum. So like if you have SI equals A1 plus A2 plus all the way to plus AI, right? If you have this, then, well, then what you see is that AI plus AJ equals SJ minus SI minus 1, right? So so this is very nice because we can kind of express all of our sums as the difference between s's and between two s's, right? These are called partial sums. Let me, I'm out of slides, so I create another one. And so, for example, S0 would be 0. There's nothing there. S1 would be 1, A1. S2 would be A1 plus A2, all the way to Sn equals the sum of everything. And we can use the same thing here, right? So like if you have I is S minus, or yeah, Si is congruent to Sj mod n. Like this notation just means that Si and Sj have the same remainder, then Ai plus 1 plus all the way to plus Aj is divisible by n, right? Because this equals Sj minus Si. Okay, so this is another important thing about Pigeonhole is sometimes you can use some sort of like partial sum, right? To like do this. So in our next example, we'll go over like we'll look at some partial, like sort of like partial sum, like the same idea as partial sum, but like in like a more abstract notion, and I'll show you what I mean. So let's say we have 2 to the n numbers. 2 to the n numbers, a sequence, 2 to the n sequence. So like a of numbers 1 through n. So this sequence only has numbers 1 through n. Show exists some subsequence. By subsequence, I mean kind of like the AI through AJ. So okay. AI all the way to AJ, where each number appears an even number of times. Each number 1 through n. By even number of times, I mean like the number 1 appears an even number of times, the number of 2 appears even number of times, all the way to number n. The number n appears even number of times. So how do we do this problem? Well, we want to use some kind of pigeonhole, right? So the idea is you want something like, you want kind of like a partial sum, but here we're not actually using like a partial sum, right? We're counting the number of times each number has appeared, right? So our partial sum SI would be, if you look at A1 through AI. If you look at A1 through AI, if you look at the numbers A1 through AI, which numbers have appeared even number of times? Which number appears even number of times, right? So in total, S of I has 2 to the n possibilities, right? Because each of the numbers 1 through n can either have appeared an even number of times or an odd number of times. So each SI has 2 to the n possible states, right? And of course, like again, like S sub 0 would be everything has appeared an even number of times because nothing has appeared yet. So what if SI is similar to SJ, right? So like what I mean by that is, if you look at the numbers A1 through AI and the numbers A1 through AJ, then each number has appeared either an odd in both sets, even number of times in both sets, or odd number of times in both sets. And I claim that if you look at the numbers AI plus 1 all the way to AIJ, each number appears even number of times. And the reason this is true is because let's look at the number k. If k appears odd in A1 through AI and A1 through AJ, then well, first of all, if it appears, let's say it appears x times here, where x is odd, then and it appears y times here, then it would appear y minus x times here, right? And if x and y are the same parity, then x minus y would be even, right? So that means that k appears an even number of times between a sub I plus 1 through a sub j. And so here we kind of used like the pigeonhole, like this partial sum version of pigeonhole in kind of a more abstract way, right? And this happens a lot in pigeonhole, right? Like you have to be kind of clever in how you define what your pigeonhole is. Okay, let's go through some other applications of pigeonhole. So we went over some more combinatorial applications. How about let's do some more like geometric ones? So like you have a square of side length 2. And you may have like seen some type of argument like this before. Like this is what most people start out with when they discuss pigeonhole. Like if you have a 2 by 2 square and you have 5 points. Okay. exists 2 points with distance. So show, this is, okay, is less than or equal to root 2. So the idea is to divide this 2 by 2 square into 4 1 by 1 squares. And the reason is because if you look at a 1 by 1 square, if you look at a 1 by 1 square, if you take 2 points in a 1 by 1 square, then they have to be at most distance root 2 apart, right? Because if you just like take the two opposite endpoints or vertices of a square, then it's root 2 already, and if you don't, then the distance has to be less than root 2, right? And by Pigeonhole we have 2 points. By Pigeonhole we do have does have 2 points in the same square. We do have 2 points in the same square, which is really nice. Okay, let's go through maybe some more examples of something like this. Okay, let's see. Why don't we do this problem? So if you have a circle of radius, radius 5, 10 points inside, then 10 points inside. Yeah. If we have 10 points inside, then if we have 10 points inside, then exists 2 points. Show exists 2 points with distance at most less than 4. And again, we want to try to split our circle, right? And we want to show exists distance less than 4. So one common thing is just to take a circle with radius 2 inside of the circle with radius 5, right? And then we can split the remaining kind of like, I don't know what the name for it is. It's kind of like a ring into 8 regions, right? And what you notice is that this is the longest. Well, first of all, you can use Pigeonhole to conclude that there must exist 2 points in one of these 9 regions. And if you take one of these like sort of like weird looking regions here, well, if you look at this distance, you can actually show that this distance is less than 4, right? And this distance has to be the greatest distance in one of these regions. And this is not that hard to show. It's just like some trig. Yeah. Okay. Okay, here's an interesting example. So we have 10 numbers, 10 distinct positive numbers. So we have 10 different positive real numbers, and they can be any numbers. Show exists 2 numbers, x and y, where 0 is less than x minus y is less than 1 plus x times 1 plus y over 9. And already it's not really clear what to do, right? Because we have 10 numbers, but these numbers can be basically anything. We're not actually told what these numbers are. And that's kind of concerning, right? Because like when you want to use Pigeonhole, you want to have like some finite number of holes, right? But how can we partition the real numbers into like 9 different sets? That's like not very. That's like not very. It's like not easy at all. Um, anyways, so like let's do some like algebraic manipulations to see like where that gets us. So first of all, I don't like how there's x and y on like two sides of the inequality. So why don't we divide by 1 plus x times 1 plus y? So we get 0 is less than x minus y over 1 plus x times 1 plus y is less than 1 over 9, right? And what you notice is that x minus y over 1 plus x times 1 plus y is actually kind of bounded, right? Because if x and y get bigger, then the bottom gets smaller quadratically, right? And the top is degree 1. So like you may be able to like kind of bound this value in the middle, right? But we still want to use kind of like the pigeonhole idea, right? We have the 10 distinct numbers. We want to somehow use that. So basically, what you can do is you can notice that x minus y over 1 plus x times 1 plus y is actually 1 plus y, 1 over 1 plus y minus 1 over 1 plus x. And now we have our x and y separate, which is good. Another thing to note is that we can actually now change our variables from x to 1 over 1 plus x, right? 1 over 1 plus x plus 1. Because 1 over 1 over x plus 1 is between 1 and greater than 0, right? And now what we have is so if we change all our variables, let's say a equals 1 over 1 plus x and b equals 1 over 1 plus y, then we have 10 numbers in 0 to 1, and we want 2 numbers with difference less than 1 over 9, right? And this is already much nicer than what we started with. And in fact, we can use the same idea that we used before, right? Because now we have something finite. So we can kind of like split it into regions like we did before. So if you have 0 to 1 in our number line, well, we can just split it into 9 parts of length 1 over 9, right? So I'm just going to draw 9 parts. And we know that 2 numbers must be in the same part. And if you have 2 numbers like a and b, then that means that b minus a is less than 1 over 9. Is greater than 0. Is between 1 over 9 and 0. Okay, so as a review on what we did today is we kind of went over what Pigeonhole was, kind of like the basics of Pigeonhole. We talked about some different strategies on how to use Pigeonhole. For example, like you can kind of think about it combinatorially, where if you have like k like things you need to put k plus 1 things into, then there must be 2 of them into that. And finally, we went over some geometric style examples where if you have like numbers, or if you have like some kind of geometric shape and you have like some points, then you can divide that region into like different smaller regions, and then you can apply Pigeonhole to that. So I hope you enjoyed today's class. Our next class will probably be like sometime next week. And also, I will be doing like a seminar on Thursday, so if you want to come to that, that's also good. Anyways, see you guys. I hope you enjoyed the class. I'm going to end the recording.